All right, thank you everyone for allowing me to be here. I hope that all of you are doing as well as possible during the pandemic. So today I'll be going over some of the spectroscopic results we've gotten from the NEP-Deep field. Okay, so first I'll start off with some background of some physical motivation for the questions that we're interested in. So we know that the infrared emission from galaxies traces cosmic star formation. And we can see this in looking at the infrared luminosity density. So that's on the plot on the left here. And as a function of redshift. And so the blue line shows the low luminosity galaxies, while orange and red show infrared luminous sources and ULIRGs, respectively. So as we look at the energy contribution in the infrared, we can see that the contributions from more infrared luminous sources becomes higher at higher redshift, around redshift 1. So this highlights the need for us to have infrared spectra in order for us to understand the cosmic star formation as well as galaxy evolution. And so what does this infrared spectrum look like? So on the right is a plot of the spectral energy distribution. And we can see that in the mid-infrared, we have a prominent dust feature known as the PAH emission. So here is a picture of the redshifted 7.7 micron PAH dust feature. And so what this tells us is that it's important for us to observe the PAH properties and connect this to dust-obscured star formation. So PAH emission is very important, as we just heard, because it is our best extinction independent indicator of the power produced by star formation and AGN. And this is especially important when we want to understand dust-obscured star formation, which is more important at higher redshifts. Especially when we can no longer directly observe the optical emission. So on the bottom here is another example of a spectral energy distribution that shows the PAH 7.7 micron feature. And this is a model from Segal. And the special feature of this image is that we can see that one of the AKARI filters is sitting right on top of the pH emission, which shows that the AKARI data are very important for directly measuring this pH emission. However, the photometric data alone are not sufficient for understanding the dusty properties of these galaxies, partially because spectroscopic redshifts are needed in order to better constrain the redshift, especially at redshifts greater than 0.8. So we need spectroscopic observations in order to get better redshifts for the models. For the SEDs. And there are additional characteristics that optical to near-infrared spectroscopy can give us, such as using the O2 doublet as a star formation indicator. In addition, we can also measure the gas extinction with bomber decrements. So for example, with using the H gamma to H beta lines or the H alpha to H beta ratio. We can also learn more about the metallicity of the galaxies using the O2 doublet, H beta, and O3 up to a redshift of 0.9. But the main goal of our study was that we wanted to see if the pH luminosity could be used as an extinction independent measure of the star formation rate. Okay, so there have been several spectroscopic observations done over the past 10 or so years. So during my time at UCLA, we've made several Keck Demos observations from 2014 to 2016. And we prioritized high redshift galaxies, so around a photometric redshift of 1. And we focused our observations on the NEP-Deep fields, which is shown on the left here, for the purpose of obtaining information from relatively higher redshifts. We also prioritized Chandra X-ray sources in order to study X-ray AGN, as well as sources with detected fluxes at 9 and 18 microns. In addition to our optical DEMOS observations, we obtained some near-infrared spectroscopy from Mossfire. And with Mossfire, we targeted strong emission line galaxies with previous optical spectroscopy. And the purpose was to measure H alpha and N2 in the J band, which corresponds to a redshift of around 0.7 to 1.1, so that we could follow up sources that had H beta O3 already measured. And then we also dedicated one slit mask to slightly lower redshift objects, so around 0.5 to 0.8, which have H alpha and N2 in the Y band. And in addition to those observations, we've also been collaborating with Goto, Matsura, and others to analyze the 2011 DEMOS observations, which is a sample of about 300 spectroscopically detected objects. And for this sample, it primarily prioritized galaxy clusters in order to study environmental effects, as well as detections at 9 and 18 microns. So in total, our sample comprises of about 500 detected objects with strong emission lines. Okay, so here's an example of some of our high-resolution spectra from Mossfire. And these objects are at a redshift of 0.8 to 1. And these are all examples of the H alpha and N2 lines. On the middle row, you can see that with the high resolution, we can actually, for some cases, see a rotation within the emission. So we see a doublet in H alpha and N2. Okay, so with our emission line diagnostics, we can classify our sources with the BPT diagram. And on the left, we can see that About half of our Deimos galaxies lie along the star forming sequence, with about a third composite and a few Seifert end liners. And so the sample includes all of our observations from 2014, as well as some Deimos data from 2008 from Takagi. And there are a few high redshift points from Mossfire, although this is not representative since we weren't able to obtain many sources with both H beta and O3. And on the right, we have another source classification diagram known as the mass excitation diagram, which plots O3 to H beta as a function of the stellar mass. And the stellar mass here is obtained from Segal fits. And this diagram is consistent with the BPT in showing that our sample is mostly dominated by star-forming galaxies. Okay, so with the spectra, we can also measure the velocity dispersion from the Gaussian fits. And so here we've plotted the velocity dispersion, which took into account the instrumental resolution. And then fit with a power law using the orthogonal distance regression. And we find that the velocity dispersion is proportional to the stellar mass to the 0.2 power, which is less steep than the relationship for quiescent galaxies found by Zahid et al. But this result is still preliminary, and we're still going to include the 2011 data. Okay, so as I mentioned earlier, we modeled SEDs with Segal. And so we combined our spectroscopic redshifts with photometry from Galax and the UV to the far infrared PAX data. And so we assumed a delayed star formation history with an exponential burst, salpeter IMF, and solar metallicity in the model. And we varied several parameters that we were interested in, including the color excess, the mass fraction of the PAH test, and AGN fraction. And so with the pH 7.7 micron luminosity estimated from Segal, we compared those estimates to our observed H alpha luminosity. So on the left is the PAH luminosity versus the observed luminosity, and on the right we have the de-reddened H alpha luminosity, assuming the Calzetti extinction law. And our sample here includes the Deimos data that had measurements from AKARI at the S11 filter. So this would correspond to redshift of 0.5, as well as the higher redshift Mossfire sample with photometric detections in the L15 filter. So the dashed line represents the relationship where the SFR of the PAH would equal to the H alpha star formation rate. And we see that at higher luminosities, the PAH luminosity curves upwards with respect to the observed H alpha luminosity. So this would suggest more dust obscuration. However, the SED fit may systematically overestimate how much H alpha extinction there is. And our high redshift Mossfire points are not sufficient enough in order to fully constrain this. So we're hoping to add more data to this plot. In addition, since it's known that the 8-micron luminosity to total infrared luminosity ratio correlates with metallicity and type of galaxy, we compared the rest frame 8-micron luminosity to the total infrared luminosity with objects on our BPT diagram. So here we limited the sample to objects on the BPT with the 11 micron filter detections from AKARI. And although that correlation is known to exist, we don't find a significant correlation here, mostly due to the small sample size. But we are working on adding more spectra to this plot. Okay, so some of our works in progress include measuring the O2 doublet to get the electron density in the interstellar medium. The spectral resolution combined with the high signal to noise ratio of our DEIMOS observations allows us to resolve most O2 doublets, which allows us to make this measurement. In addition, we would like to analyze the QPAH parameter and the AGN fraction from Segal and see how those vary with our spectroscopically confirmed AGN. And we would also like to connect our emission line diagnostics to R-band megacam images in order to look at the morphology and galaxy interactions. And that's my talk. Thank you.
Okay, thank you, Helen. But we don't have enough time to Q&A, so you can ask.
You can ask.
Okay. Good. So there is a question. Question is this: power versus H alpha is not on X or Y luminosity dependent. So this is from Thomas.
Yeah, so the redden luminosity of H alpha and then PA8 doesn't seem to be X equal Y. So is it luminosity dependent? Is that expected? Helen, did you hear my question?
Sorry, can you repeat your question?
Yeah, so on the right side of the plot, it's not X equal Y. So does that mean like it's luminosity dependent that I don't know, maybe pH to star formation rate conversion?
Right, so those aren't actually one-to-one. So it's that the star formation rate is equal to the of the PAH features equal to the star formation rate of H alpha. But on the plot, I'm showing the luminosity.
Is this expected?
I think so.
Maybe if the PAHs are getting destroyed in very luminous starbursts, I mean, like you see in ULERGs sometimes, I don't know, is it a possibility?
Right, so we do think that's a possibility. So that's why we suspect that there would be some depreciation of the PAH when the H alpha is higher. But we're still investigating that. So
if I look at the very old Kennicott relation, then the slope is 1 for both PAH luminosity and H alpha luminosity to the standard rate. I don't know up to date results.
Okay, thank you. I'll have to check that.
Yeah. Helen, you can see your corresponding threads under your